Okay, so where were we? Drawing rectangles, right? So the red line is my spine together with the places where the building, not the building, the dome is going to touch the ground. And the black lines are where I'm going to have the rectangles, which are going to be touching via one edge perfectly, right? So I'm just drawing out these kind of rectangles to just get an idea, right? Like that, and something like that. Oh, missed that one, but yeah, you get the idea. So we end up with 1, 2, 3, 4, 5. We end up with 6 rectangles, right? Going back in Rhino, let me do this exactly same thing. So I'm just going to, first of all, take a line, take a cascade, I don't know how it's called, expand the lines, the lines toolbar here. And I'll just find a tool that's called line from midpoint. So it's the third one in the list, right? So if you expand the toolbar under polyline, if you expand that one, the third item or the third tool on the list is line from midpoint, right? This guy. And then I'll make sure that I'm still drawing in the helper layer, and I'll just draw out those legs, right? This, and this. Something like that. Okay. Now I don't need to use that line from midpoint anymore. And I can continue working with within the default layer. So then I will just use a simple polyline and just kind of draw out the rectangles. Just make sure that they are connecting perfectly. I mean, that there are no weird gaps and so on. So with this approach, the restriction that you have is that you need every curve, every polyline to be a closed polyline that has 4 corners, right? So we're dealing with we're dealing with 6 rectilinear curves. Okay. I'll just give you a second. This is an important thing, so listen up. When you finish drawing the rectangles, just hide the helper layer so that it's just these 6 rectangles that you have on your screens. All right. Once you have done that, reference in these rectangles as curves into Grasshopper, right? So just create a curve component in Grasshopper, empty curve container in Grasshopper. The one that has the hexagon icon, black hexagon icon. Right click on it, set multiple curves, select your curves in Rhino, hit enter, and you're good to go. So since we're going to be working with Kangaroo, the approach is going to be quite similar to what we have been doing yesterday. with the mesh relaxation. At least the building of the mesh part is going to be exactly the same, right? So I always say repetition is the key, you know, to learning things. Wax on, wax off, right? So time to repeat it. We have our curves, and all of these curves are flat, meaning we can use divide surface tool. Curves go into surface input, and for U and V divisions, we will be using the same number, right? So for U and V divisions, the same slider, sorry. So for U and V divisions, I will be using a slider that's between 3 and 12, I don't know, between 3 and 12. So 3 dot dot 12. Enter. You have a slider. Connect it to U and V. And now you can fully control the density. Your surface divider might turn, yep. Remember when I said that the helper layer should be turned off? It might be that, wait, let me see. Yes, it absolutely has to be closed lines. Okay, let's see. Oh, this is gonna be fun. So, first things first. If it's not working for you, clear values. So right click on your curve, clear values. Then make sure that all that you have on your screen is 6 rectangles. Let me explain it better. This is not a rectangle. This is a rectangle. If you have 6 not a rectangles, then you can select them and type in close curve. And it's going to force the rectangles to close. Also, yeah, make sure that you turn on the end snapping, endpoint snapping when you're drawing the rectangles, just so that they all connect perfectly. So, one by one, if you still have problems, select one rectangle, set it as one curve. Check if that works. If it works, clear values, set 2 rectangles in Grasshopper. Check if that works. If that works, set 4 rectangles. And eventually you'll see if there is a rectangle that's not working. And then you just, for instance, let's say this guy right here, let's say, let me delete that, join that, move that, set multiple curves. There we go. So you can see on my screen that right now I have red surface divide, right? As if it's not, you know, it cannot do something. And I can tell that there's something wrong with this guy right here, right in this area. So if I select it and kind of drag it out for a bit, I can see that it's not a closed curve, right? So I can just select it and type in close CRV, enter, and now everything works. Oh, if you zoom into 1,000th of a millimeter, then it's you're going beyond the tolerances units. You're going beyond this tolerance, or you're going really close to the absolute tolerance of the project, and then it's going to stop displaying everything correctly. So don't do that. Mm-hmm. All right. So does it work for everyone? Mm-hmm. 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 Your points don't line up in the middle. How? Okay, are you using the same? Make sure that your slider that you have here is connected to both U and V inputs. And then as long as the rectangles line up, yep, good. As long as the rectangles line up, it's gonna work. Okay, so we have our, this is how we can change the resolution. Sweet. Now we move on. So now we have a bunch of points, and this is the moment where we used to use the trim tree tool. Trim tree, and we just connect the output of our surface divide to the trim tree input. And again, to repeat what it does, we have, what we have here is 6 rectangles, right? Which means that originally the surface divide will give us 6 initial branches corresponding to 6 of our rectangles. And then each branch will, well, in my case, it will have 11 sub branches or 11 smaller branches, which correspond to the rows of points within each rectangle. We don't want those points to be divided up into rows, which means we can use this tool that's called trim tree and get rid of that row and column information in our grids, right? So that's why we're using the trim tree, and we are only left with six lists of points, rather than whatever 66 lists of points. Okay, time to make a mesh, I guess. So to make a mesh from points, we use a tool that's called mesh from points. Mesh from points. And we just connect the trim. Oh, yeah, and those of you who can use mesh from points, actually, let me show it with both of these tools, and let me show the difference between them. You know, mesh from points and the Lund mesh. So if I connect my trimmed points to my Delanoy mesh point input, you can see that I get this kind of triangulated mesh, right? So everything is constructed out of triangles. The way it works, it kind of measures the distances between the points, and it will generate a triangular mesh for us. And it's fine. Delanoy mesh is fine. It works. So those of you who cannot use mesh from points, just use the Lonoy mesh. As long as we're not, as long as we're not doing something similar to Armadillo Vault, it's absolutely fine to use. If you can't see the triangles, go to Display, Preview Mesh Edges, or type in Control M. Not type in, but use Control M. Yeah. So that's the Lonoy, and it's quite, you don't need to do anything with it, anything else with it. It just works. Mesh from points, though, is a bit different because it retains the information of what point comes after, of the series of points, right? So all of them are kind of sorted, while in the Lonoy mesh, the points get scrambled around and they become quite randomized. So mesh from points is a much more controlled, let's say, way of how to construct a mesh. But for this tutorial, for instance, for 3D printing, both of these would work exactly in the same manner. But when it comes down to, later on laser cutting and so on, it's better to use mesh from points. Anyway, so the Lonoy mesh, you just straight up connect. Mesh from points, you also connect the trim output to the point input. You connect your slider, which you use to control the resolution, into U and V inputs. It will turn red. And that is because, I really like repeating this part. And that's because if you have, let's say, 4 divisions, 4 subdivisions for every rectangle, it's going to actually give you 5 by 5 points, not 4 by 4 points, meaning that mesh from points needs to receive one more, like value that is by 1 larger than what the slider says. And we can do that by right-clicking on the U input, right-clicking on that, going to expression, and typing in x plus 1. Commit changes. And same thing for V. X plus 1. Commit changes. And we end up with a mesh. Well, not actually a mesh. I'm, by the way, hiding everything except mesh from points. Oh no, running out of time. Okay. So apparently, yeah, that's fine. For tomorrow, I will just get the pro version of Zoom, and then it won't bother us anymore. So the output here from the Lonoy mesh and the output from mesh from points is basically the same thing. It's just a different form of it, but it is quite the same, right? In the way it works. So those of you who are able to use mesh from points, continue on using the output from mesh from points. Those of you who can't, use just the output from the Lonoy. So right now, actually, let me do this. Right now, the output that you see is still separated into separate branches, right? So this is not a single mesh, right? This is not a single mesh, but rather this is 6 separate meshes. We need to join those up. And I can use, first of all, I need to get rid of the data tree, right, of these branches. So I can just right-click on the M output and choose Flatten. And now all of my meshes, and same thing for the Lonoy, Flatten. All of my meshes are in the same list, right? So now they can see each other, which means they can be joined together. And let me yesterday what we've done was we've used mesh join, and then we used mesh weld vertices, like these two components. Today instead, let's use combine and clean component. Combine and clean. Good. And also together with combine and clean, let's use unify mesh, mesh unify normals. And then hide everything except mesh unify normals. You should see a pretty clean mesh. Those of you who cannot, I hide it by just selecting the nodes, clicking the scroll wheel, and choosing to disable preview. Pum, pum, pum. Okay, so the first node is combine and clean. If it doesn't have the red square pattern, use Control M in Grasshopper, and it's going to show you the polygons. Or just go, yeah. Yes, and the next one is mesh unify normals. It can be found in Weaverbird, somewhere here in Weaverbird. Extract. Where is it? No, I can't find it. Yeah, just type in mesh unify normals. you're gonna find it. Hmm? Mm-hmm. So, works for everyone? Can't find it. Mm-hmm. It's not in Weaverbird. It's in the, sorry, didn't realize that it's actually in the utilities. Sorry, under mesh tab in utilities, and it's mesh unify normals. This guy right here. You can also use unify mesh. That would work as well. Okay. Then more questions. Could you show what boxes you connected to from points in the UVC? Oh yeah. I connected the slider, and the key thing is that U and V need to be. You need to right click on U input and V input. Go to expression and type in x+1 for both U and V. Okay, that's good. Olivia, I believe, yeah, and Olivia didn't have the mesh from points as well. So that's the part of the same plugin then, I assume. That's fine. Use the, we can work around this. So for, we can have a second group here. So this is the class and this is Olivia, and Olivia is doing clean. Combine and clean, and she's doing unify mesh rather than unify normals. It should be the same thing. Let me just double check. Bake. Let me double check here. Yeah, so it's going to work well. So Olivia, you just used the unify mesh. I hope that's not a part of the plugin as well. Yay! Okay, cool. So we move on. So we have right now we have a single clean mesh, and we can control the resolution of our clean mesh with this slider, which is really nice. Moving on, let's see. Yeah, let's push it a little bit more, like 8 more minutes, and then we'll have a quick break. Measurement points, but I don't see the triangles. Control M, not L, M. Or if you can't remember the shortcuts, it's in the top under display, preview mesh edges. Oh yeah. Okay, so let's have a 15-minute break, and then we'll continue. Okay, I will get everyone in the call after the break. Right, so 15 minutes. Chords. Okay. Fruit cocktails. Good. Okay. So let's continue. Now we have a clean mesh, which we can use in any way we want. And in this case, we're going to be creating a dome shape. And for that, we will be using Grasshopper, right? For that, Kangaroo. Well, Grasshopper as well, but Kangaroo mostly. So if we go to the Kangaroo tab, make sure that it's Kangaroo 2 tab. We go to main and we put in the solver, right? So just the solver. We want to make sure that it's not a zombie solver or not a bouncy solver, just the solver. And it's going to be quite the same thing as we've done so far, right? So I'm leaving a bit of a gap between the mesh and the solver because I'm going to be putting quite a few nodes here in between. What? One person is missing? Who's missing? Olivia is missing. Olivia K. Okay. Wait. Oh, I can do that. Nice. Anyway, one person is missing. Olivia K. Let me find her. Olivia Nilsson is not, N is not K. Oh, I can't. Let me just invite to meeting and also invite Olivia. There we go. So now it should all be good. That's good. So now we continue. Let me minimize that. Double check the chat. What? No, that's fine. Your microphone was not muted, but I've just muted everyone's microphones. If you want to unmute it, you can do that through the Zoom app screen. So we have the solver here. Again, Kangaroo 2 main solver. And we can start adding nodes to it, just like we've done yesterday. So for on or off, again, that's a toggle, Boolean toggle. So we can turn it on or off, turn on or off the simulation as we please. Tolerance and threshold, I still will not be showing what it's doing, so we will be ignoring those two. Reset is a button, so type in a button, plug that one in, that's your reset. And goal objects is a series of goals that the solver needs to achieve, right? So since it's a series of goals, we will be using entwine. This thing here. Because basically, let's say you have a goal for the contraction of the mesh, right? So yesterday we had a mesh that needed to try and contract to have least amount of area possible. The way that goal works is that it takes all of the lines, all of the edges of the mesh, and it tries to shrink them to 0 size, meaning that there's a list of edges that are trying to contract. And then you have another goal, which is anchors, for instance, points that cannot be moved. That's also a list of points that need to be locked. So what Entwine does, it takes those lists and builds a data tree, a list of lists out of them. Let me just check the chat. The flatten. Here, you just right click. Wait, not there. Where? Flatten was only used here as in the Entwine. It should be by default because Entwine works with if you right click on the name Entwine, you can either tick mark flatten inputs or untick it, and it says graphed then. Yeah, if you're zoomed out, it doesn't show, but if you zoom in, so by default, it's set to flatten. It's basically, if you're plugging in a list of lists, a data tree into one of these inputs, then it's going to treat that input just as a single list, right? So you're reducing complexity a little bit with this. Just next. Okay, so our goals. It's always, like the first goal is always show, right? Because we always want to show geometry. So I type in show and plug that one into 0, 0. And then what are we going to show? Well, it's our unified mesh, right? So from unified normals, we just connect it to show. If you don't have the plugin, then you use the result of Unify Mesh of this node here. Right, so it's either this or this, either one of these two. Okay, so right now the simulation, just like yesterday, the simulation would go, since there's only one goal, which is show, the simulation would go, once we run it, it would just say, here you go, there's the mesh, and that's it, end of simulation, because we're only asking it to show the geometry. So the next thing is we want to be able to control how much does the mesh contract, right? Just like we did yesterday. So for goals, so to contract the mesh, we can go to goals mesh. That's also in Kangaroo too. And we can choose edge lengths. Like that. Right? Asks us for, well, first of all, let's connect the edge lengths to the 0, 1 input of the entwine. Like this. And also we need to start plugging in stuff to the edge lengths node, right? So mesh, well, that's our unified mesh, right? There. Length factor, though, is, again, it's a factor. It's not the actual length of each edge, each line on the mesh. It's rather a factor. So it's a proportion between 0 and 1, right? If it's 0, it's going to try and contract to 0. If it's 1, it's going to, each edge will try to keep its original length. So for length factor, we need a number slider that's between 0 and 1. I will just type in just a single number, 0.500. The more, not 0.500, but 0.500. So it's just a half, 0.5. The more numbers you type in after the comma or after the point, the higher the resolution of your slider is going to be, right? So 0.500, plug that one into length factor, and let's see how it is going to work, right? So I'm going to reset and run the simulation, and you can see the mesh contracts. Actually, let me hide everything except the solver, just so that it's easier for you to see. And I'll hit the reset button again. Right? You can see how it contracts. Each edge tries to contract to half of its original length. If it's set to 1, it's not going to contract at all. It's going to just stay the same. Or if it's set to 0, everything is going to contract to, a single point. So for now, I'm going to have it as 0.5. Like that. Make sure that the simulation is turned on. So the toggle is true. Yeah. So now, once we know that this whole thing kind of works, I will be turning off the simulation, so toggle false, and hitting the reset button, right? So that it's back to its original, the starting condition. Your button does not work. Are you talking about the toggle? Or are you talking about the button? Because you have the button here. The reset button doesn't work. Wait, what? Okay. Let's think. First of all, if there is no dashed line from entwine, go to display and choose draw fancy wires to be turned on. Does that fix the dashed line not being there? Okay. Then the reset button doesn't work. So let's see. If I turn on the simulation, so you can see the simulation is running, and I hit the reset button, it's just for a second that it will kind of reset, right? And then it immediately will start running the solver. So make sure that you, for now, for the next steps, make sure that the simulation is turned off, right? So the toggle is set to false. And when you hit, then when you hit the reset button, it should kind of jump back to its original form, how it was before. Okay, good. So now we continue. So now we can control how much we are contracting the mesh, and now we are saying that it should show it. So next thing is, just like we've done thus far, is anchors, right? So we need to specify which parts of the mesh are locked. And in this case, like previously, what we've done is we've just said, yo, give me the outer perimeter of the mesh, right? And lock the outer perimeter, all of the points around the outside, outer perimeter of the mesh boundary. In this case, we don't want that. In this case, we just want just the points which are here, here, and here. Only these points we want to be locked. So we will need to do some Rhino Grasshopper shenanigans to achieve that. Back in top view, I will just create a polyline. Well, let me minimize Rhino for now, Grasshopper for now. In top view, I will just create a closed, it's very important that it's closed, a closed polyline, like so. Basically, I will draw either a rectangle, doesn't matter, as long as it's a closed polyline, it's gonna work, around the points which I will want to lock in place, right? So something like this. And I'll repeat it for every leg of my shape. Something like that. So we have 3 additional rectangles. All right. Okay. Back in Grasshopper, I will reference these 3 additional rectangles as curves. CRV, enter, right click, set multiple curves, click, 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 enter. So now we have them in Grasshopper. Okay. I'll give you like 10 more seconds to do that. Now, we have the curves here, and we kind of have the mesh. The problem is that the only part where we kind of see the points of the mesh, the vertices, is in the solver. And we can't really connect the points from the solver into anchors, because it would make this kind of infinite loop of information, which doesn't make sense to do. Instead, where we have our unify normals mesh, right, the output of unify normals, I can extract the points from that mesh, all of the points, right, from that mesh, by just using Weaverbird's vertices component. Shortcut for it is WBV. Weaverbird's vertices component. So WB is for Weaverbird and V is for vertices. WBV. Enter. This node gets created. If I now plug in my unify normals output to my vertices component geometry input, G input, and I select it to highlight, stuff that it's creating, you can see that it has extracted all of the points from my mesh. All right. Now, next step is checking which points that we have just extracted are inside of our drawn regions, these kind of 3 drawn rectangles that we've done, which points are inside and which points are outside. And we will want to choose only the points that are inside of the rectangles that we have drawn, or the regions that we have drawn. So I will ask, I will type in point in curves. Be very mindful of the fact that there are 2 types of tool like this. There is point in curves, plural, multiple curves, and then there is also point in curve, singular. If you choose point in curve, it will not work. You need to choose point in curves, because we're using more than one closed curve for this to work. Point in curves. Asks us for 2 inputs. First one is point, second one is curves, right? So from our Weaverbird vertices component, we have the points, so we can just connect them. Points go into points, curves go into curves. Just give you a second. Okay. What we get from this is 3 inputs. One is relation, the second one is index, and the third one is projected point. We don't care about the index or the projected point, we care about the relation. If I hover over the R output with my mouse, I can see that it says point/region relationship. If it's 0, the point is outside. If it's 1, the point is right on top of a region curve. And if it's 2, it's inside. Honestly, what we care about is just the zeros, right? So only the stuff that is outside. Thankfully, in not just in Grasshopper, but also in most of programming, 0 is considered to be false, and anything other than 0 is considered to be true. And we can use that to our advantage, right? So if point is outside of the curve, it immediately receives a false statement, right? If point is inside, let me explain it here. Right, so let's say we have points. Doesn't matter. Point, and we have a region, right? So this point receives a false. This point receives a true. This point receives a true. This guy receives a false, and so on, right? So what we can say in Grasshopper is take the whole list of points, you know, all of these like blue points in this case, and remove everything that says false. Just leave the things that say true. And thus we would just keep the points that are directly, well, let me do it in the blue color. Then we will just keep the points that are directly inside of our regions. Removing stuff in Grasshopper is called cull, C-U-L-L. And there are different ways of how you can cull things. In this case, the one that, and it's mostly used like for various applications. We will be using cull pattern. Pattern is these kind of true and false statements, right? So cull pattern, we use that. And it asks us for two things. It asks us for a list of things that you want to, from which you want to remove stuff. And it asks you for a pattern, right? So if I connect my ViewBird vertices output to my list, that means I'm removing stuff from my whole collection of points. And if I'm using the relationship output of my point in curves component, it will use that as true and false statements to remove the points that are outside of my curves, right? So then if I select this cull, after I have connected everything, I can see that only the points inside of my regions are selected, meaning that only those points have not been deleted from the list. So now I'll wait and see if any one of you, when you highlight cull, if any one of you gets some, you know, discrepancies from what you see on my screen and what you see on your screen. Cull pattern. Olga is typing faster than I speak. Well, I guess most of the people are typing faster than I speak. So. I assume it works for everyone. That's good. Okay, so these guys right here, the culled points, are going to be our anchors, the points which are locked in place, right? So we will be using in Kangaroo 2 goals point anchor. We will be using anchor node. Just like that. Anchor asks us for point to anchor. You know, what kind of points do you want to lock? So that's perfect. We just connect our cull to our point input of the anchor. it asks us also for the target. And the target is basically if you want to anchor the points, but also you want to move them to a certain place during the simulation. At this stage, we don't need to, so we will not. But sometimes it's a very, not sometimes, it is a very strong tool to be able to use. In some cases, we will be using it later. And then strength for anchoring. And oh yeah, speaking of strength, for instance, edge length's strength is by default set to 1, right? While anchor strength is set to 10,000, meaning that even by default values, it's the way Kangaroo is written is that anchors don't move, right? When they're locked in place, you need a lot of force to be able to move them around. Okay, so we don't need to, oh, nice. So we don't need to add anything more to the anchor node. We can just simply connect it to the 0, 2 input of the entwine, like that. So that's our third input. Let me hide everything except the solver again, right? So I'm as you can see here from what's gray in my definition, everything is completely gray except the solver. And now I will just make sure that it's working correctly. So I'll hit the reset button and I'll toggle true for the solver. One. And it relaxes, right? So it stretches like a stocking material would stretch, right? Or any stretchy fabric material would stretch. Jiggly. Yes, it's also, yeah. The jiggly part happens because at the start of the simulation, there's a lot of pre-stress. There's a lot of, a lot of stress in the structure. So when you hit go, when you hit the toggle true, it shoots out the vertices, the points of the mesh too fast, so they overshoot the target, and then they kind of find their equilibrium point later. And I'll be talking about equilibrium moments in a bit, but now at least we know that it works. We are still working completely in 2 dimensions, and this is the moment where we are actually going to move everything up, right? In the 3rd dimension. So I'll switch to perspective view like this. I will turn off the solver. So toggle false, and I'll hit reset. So now we're back to normal. Let's see. Is it something like, this? Okay. Notice what I have done here. The corner point doesn't align with other corner points of the rectangle. That means you haven't snapped it properly. So if the rectangles are not aligning, it's going to start making holes for you. So the way I work with it is usually I just go through. Oh, fixed it. Nice. So but it's basically I just go through every rectangle and just make sure that everything kind of aligns. Grid snap, if you have grid snap turned on, it's really bad in this case, because it might kind of snap to the grid line rather than the endpoint and kind of mess up your whole structure. So make sure that grid snap is turned off. Okay, so I turned off the solver, I reset the solver, and we're back to normal. And now it's time to add one more goal. So where you see entwine, if you zoom into the entwine node, you can see these plus and minus signs. If you click on the plus sign right at the bottom of entwine, it will give you one more input. So this is how you can control how many inputs you're actually using for the entwine. So I'm just adding one more input. Again, you won't be able to see it if you are zoomed out, but if you zoom into the node, you will be able to see the plus and minus signs. So I've added one more input, 0, 3. Okay, and for that input, I want to apply gravity, right? So Antoni Gaudi did hanging chain models with unfortunate gravity pushing downwards. So he had to later on flip his images, that he drew from the structures. In our case, we can say that gravity is up, right? And it's not down. So we'll do exactly that. Under goals point, no, it's not under goals point. Sorry, it's under goals mesh. Goals mesh, vertex loads. Apply equal vertical loads, basically equal vertical force, to all vertices, all the points of a mesh. Vertex loads, we use that. So we connect vertex loads to our entwine, the new input of the entwine that we've just made, like that. Yeah. And then it's asking us for a mesh, and we constantly keep using the same mesh, right? So it's the mesh from unify normals that we get from unify normals. We connect it like so. So unify normals connects to vertex loads. And then you have strength. If I hover my mouse over the strength input, I can see that it says minus 0.1, meaning that it's going to be pushing downwards as if gravity was at play by a low amount of strength, 0.1. In this case, we want, but wait, this is weird. Or is it? Let me just check. I will run the simulation, hit reset. Yeah, it's hanging down. Yeah, so it is not weird. Okay. So in this case, for the strength, let's use a slider that's between 0, ... and 2. Enter. Right? So we have a slider that can be 0, 1, or 2. It's not enough resolution of the slider, right? Because we can just, kind of have no force, 1 force, or 2 force. We want to have much smoother way of how to change this. So I purposely made it like so that we now need to right click on the slider, and we need to click on edit. And here, where it says rounding, we can choose, instead of choosing integer numbers, we choose floating point numbers, R. So numbers which have digits after the comma are called floating point numbers. And I don't remember the exact amount of how many digits after the comma you can have, but I think it's like 16 or maybe even more. So you can go pretty far with it, or maybe even more than 16. I don't remember. Anyway, when you choose rounding to be floating point numbers, you can change the amount of digits after the comma that you'll have. So in this case, I will just choose 3 digits after the comma, hit OK. And now you can see my slider can go at much higher resolution. It's still in between 0 and 2, but now I can control it much, much better. So I will connect the slider to the strength, and right now the strength is set to be 0. About it. Let's see. Testing, testing. Seems to be fine. Okay. So now we have our dome shape kind of working. Honestly, that's it, right? Now we'll just make it pretty, and then all that matters is how you arrange the, these kind of starting conditions. How do you arrange the patches, and how do you arrange the rectangles for anchoring? For instance, here, if I were to say that, no, my rectangle, for anchors needs to be here, it's going to lock these points in place, right? Or it needs to be here. It's gonna lock it like so. Don't do that. That's quite disgusting. Keep it simple. Every time when it messes up, just hit the reset button and it should continue working quite well. So now making it pretty. First of all, the output of the solver is a data tree, and we only need to extract the first branch of the data tree, which is show, right? Which is the mesh. So I will be just using the explode tree node, and connect my solver output O to explode tree input. And I will be zooming into it and removing the 0,1 output, so that I only have 0, 0. Yes. Yes. Humorous. Yes. Anyway, so once I have removed 0,1 output and I only have 0, 0, it's just the mesh that is coming out from here, right? Which means I can now hide everything. Like literally, I've just hidden the whole definition, right? And I will just create an empty mesh container and connect my explode tree output to my mesh container here, like that. And now we can make it pretty, right? We can use custom preview, like that. We can use swatch, not switch, swatch, like that. Connect it to material and change the color to something like this. Chat. I hid it. I hid everything. No, there's no need to clean again since we've done that part here. So you can either do it before the simulation or you can do it after the simulation. In this case, we just did it before. Oh, there we go. Zoom has recorded. That's good. So this works. The previous custom preview. Custom preview and also color swatch. So now we can play around with it, right? Because here it's a pretty boring one, you know, three-legged dome, which is very traditional. Actually, where can I find the stuff that you've done in AAHO? Olga has been doing some cool stuff. And while she was studying in Oslo and Aho, I think it's going to be in here, projects. There we go. So these kind of dome shapes, right? So you can see that this was indeed done with Kangaroo. These dome shapes were done in Kangaroo, but the thing that makes them really cool are these holes, these kind of inner courtyards of a dome shape, right? These kind of light wells, because they kind of start framing the space, but also they are an opening, right? So they introduce light and so on. So it's quite an interesting or beautiful thing, at least for me. So if we want to do something like that, let me just delete all of it. Delete the helper. And let's think, right? So when I'm thinking, I'm usually drawing, right? Rather than drawing in Rhino. I'm drawing it either in Photoshop or with a pen on piece of paper, right? So we need a hole, right? And we need some sort of a cool structure. So if I have a rectangle, like one rectangle like so, and let's say my whole opening is here, right? How can I make this into a into a shape that's made out of rectangles? So let's start thinking about it. If we have that, then we have that. Can we? Don't remember anymore. So something like that. So if it's 3 rectangles here, oh crap, I don't remember. Olga, help. Do you remember? The division, because I don't remember. But yeah, that's fine. I will sketch it out. Bear with me. Oh, that's very thick. Less. Yeah, that's good. So let's say I want to have an opening. Let's see, there's a square here, square here, square here, something like that. And then we have a square here, square here. Then we have a square. Okay, so we start off with this, and this becomes an opening, this area right here. And then we can kind of start messing with it and introducing these kind of slabs. Can we do? Okay. At least I have I know that it doesn't look like much, but at least I have an idea of how I'm going to do it. So let's say, let me just freehand draw this way in Rhino. So let's say we have a square, right? That's doing something like this, and then we have another one that's doing something like this. Another one. No, I've just deleted my inputs. So Grasshopper is still here. It's only that I have deleted everything in Rhino, and I'm redrawing everything from everything within Rhino. I'm just showing you how to make a different shape. So right now I'm just going to make something quite simple. Something like that, maybe. No, that's boring. Let's do hexagon. I will just lock it so that I later don't accidentally select it. And you, of course, you don't need to follow it. Just I'm just showing this to show you the way you usually work with these kind of structures, like the way you think about these kind of structures. You can either just draw it as series of patches, like these rectilinear patches, or you can draw it as we did before with spine and then kind of beefing up the red spine. It's absolutely up to you. So for instance here, let's say I want more meat on this leg and I want more meat. Can we do this? Why not? Something like that. So let's say I have this kind of structure, right? Let me just reference it in. And then I will just, oh yeah, make sure that you stop the solver so that it's not kind of calculating geometry before you don't want it to be calculating geometry. I need to choose which parts are being locked in place. So that's ViewBird vertices component. I enable the preview of that and I draw around. So I want to lock these guys. I want to lock these guys. Want to lock these guys. And I want to lock some sort of a, I don't know, maybe this area right here. Something like that. So I have these regions here, which I can simply select. Set multiple curves. Go back to perspective view. And just see how it works, right? So the structure that I get is, looks like that. I can kind of start messing around with it a little bit with control points. And so on. Yeah, and we end up with something a little bit more similar to the, where was the armadillo pavilion? To this dome here. It's just that this dome has 2 holes and 1, 2, 3, 4. It has 4 contact points or 4 contact edges and 2 holes. We have 3 contact edges. Well, no, we do have 4 contact edges. It's just that we have a single hole. But I hope you get the idea. The thing is that it's not just Philip Block who's working with these kind of structures. I've already shown you Mark Fornes last time. Are we recording, by the way? Yes, we are. I've shown you Mark Fornes yesterday, but I will come back to him here because he's not just using the relaxed mesh approach, but he's also using this kind of catenary dome approach. Sorry. Let me just find, yeah, for instance, stuff like this, right? It's absolutely the same approach as we're using right now, only that he has much more patches here. Like in this dome. I'm just trying to find, oh, that's a cool model. Anyway, let me just try and find it. Okay, this one doesn't have any diagrams. I just want to show you a diagram of it. Come on, couldn't find the page. That's cool. So that doesn't work. Yeah, for instance, this guy. You know, a concert hall dome, right? It's just series of these kind of rectangular patches, right? Nothing more. Oh, there we go. Oh, and the interesting thing that they're doing here is instead of contracting the shape, they're inflating the shape, right? So let me show how we can do that. I'm not sure if it's going to work in this case. Oh, it kind of works. It's not the nicest though, because it's starting to buckle a little bit. But if our length factor would be 2 rather than 1, oh boy. Okay. we need a little bit more polishing with this approach, but it's basically they're choosing the edge lengths to be larger than 1 and then introducing a certain amount of smoothing and so on. So it's a much more complex definition that they have, but it's kind of the same approach, right? All aluminum. Anyway, hope that does it work, by the way, for everyone? You know, this kind of a structure. Bricks. Bricks how? Bricks like no. I'm just talking overall. Not necessarily this structure, but the definition itself. Okay. If it has a lot of holes, that means you will need to realign the rectangles, unfortunately. Let me show you one last thing. Let's say you want to put a hole right here. Let me make it red. Right? You want a hole to be right here. There is no, first of all, if you're using triangles, you know, if you'll start drawing out triangular shapes like this, it will not work. Every single patch that you do needs to be rectilinear, meaning it needs to have 4 corner points. If it has 5, it will not work. If it has 3, it will not work. That's the limitation. It is possible to make it work with 3 or 5 corner points, but it's first be able to use, you know, this definition well, and then if you need to, we will be able to implement more functionality to it. So back to here. If you're using, not if you're using, but if you need a hole to create a second hole, then what I would do is I would select these 2 curves, which are, you know, kind of, which will need to be changed. And I will just change their layer to be red, right? So right now they're in the helper layer. And then I will draw on top of them. So I'll draw out how I think that this should work. And first of all, let me do that in Photoshop, because it's going to be much easier for you to see in Photoshop. So what we have here is we have a rectangle. We have one rectangle here. And we have a trapezoid rectangle. Something like that. Whoop. Whatever. We have a rectangle, right? And we want to make a hole here, right? So we need to rebuild this whole shape out of patches, which are rectangular, which have 4 corner points. So let me just choose a blue or red color and let me draw on top of it. So first things first, I'm just thinking. Okay. First things first is this rectangle here. It's pretty easy, right? We just have a rectangle there. Then we have shape here, 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 and here. We have a second rectangle. Then we have, well, a third rectangle, fourth, fifth, sixth, right? So the rectangles can be quite twisted and they can still work, right? So let me do it here. First rectangle, here, 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 and here. Second rectangle, here, here, and here. Third rectangle, that's good. So third rectangle is going to be problematic, right? Let me just turn off all of the unnecessary snaps. Okay, so the third rectangle is going to be from here to here to here to here, right? So this is our third rectangle, and you can see that this area right here is not a convex corner, but rather a concave corner. It means it's going inwards, right, into the rectangle. This will not work. It needs to be, this is another limitation. It needs to be concave rather than, convex rather than concave. Meaning I will just hit F8, F10 to get the control points. And I'll just move the control points like so that this rectangle right here is all of the corners of it are sticking out, right? That's important. So now this works, and now we're left with three more rectangles, right? So I have one here like this, one like that, and one like this. So I've just drawn exactly the same thing as you see here, right? I've just divided it up into rectangles. Now, just to keep things clean, I will make sure that I don't accidentally select the helper lines. So I'll just right click on the layer of the helper lines, select objects, delete, just get rid of those. And then I will select all of my patches, all of my rectangles, and kind of reapply them here. Set multiple curves. Ooh, why are you angry? I messed up somewhere. There we go. So this guy right here, I messed up with this one. You can see that it's an open curve, right? There's no segment here. If I type in close curve, then this one stops complaining, right? Because this gets closed and now it can work. Okay. Yeah, let's just see how it looks like, right? Perspective. Enable the preview. So now we have a hole. Right. So the more you will practice, the more you will work with these shapes. And this applies, by the way, everything that I'm showing here and why I'm repeating it so many times is because it applies to our previous tutorial as well with mesh relaxation. The more you work with these kind of rectangular patches, the more control you will get, the better you'll understand what the heck is going on and how do the shapes connect, and what do you need to do to make them work. So it's honestly, like, from experience, it's trial and error, right? You just try it out, you find something that doesn't work, you fix it, and then you know how to fix it for the next time, right? And you keep building up that knowledge base when working with these structures. As you can probably guess, these structures are pretty much, like, they are widely used, and they're really, really beneficial for quick and strong pavilions. Oh, that's good. 10 minutes. Oh, that's perfect. So after 10 minutes, we'll have a lunch break. So for me to just wrap things up here with this tutorial, with more resolution, you also have more control. For instance, let me delete this one for now, just for a bit. And since we have now 3 patches here, rather than 1 patch, like here, what we can do is we can start creating this kind of a curve. Well, not a curve per se, but something that is a little bit more, a little bit less rectilinear, right? Something like that. While with these ones, we can't. With these ones, all of your anchor points will need to be aligned in line, in a single line, right? Here, because you don't have enough control points to move here. Here we can have control points doing something like an arc, right? And I can kind of select them, not select them, but rather draw a new polyline around them. Ooh, can we do something funky here? Come on. Like that. Like that. Maybe here. I want to lock that part as well. So as you can see, I'm starting to play with it, and I hope that you will too, right? You just, play around with it and think of, what would be a cool behavior to have with these structures. What if these points are, oops, what if these points are kind of here, this is kind of here? Then we have a door. Anyway, I'm having too much fun here, so I'll stop now. But that's how you work with this definition. Questions? before we go for lunch. Of course, I will be. Since we still have like 5 minutes or a little bit more than 5 minutes, let's group things up, and I'll show you how to clean things up so that you can tell what's going on once you open it up again on Thursday, right? So I've already kind of talked about this yesterday, but now we're just going to do it. First of all, I'll go through all of the nodes, right? So curve, surface divide, trim, and mesh from points. It's basically we can just select curve, surface divide, and trim, group them. So you select the 4 nodes, you click the scroll wheel, and at 12 o'clock you'll see the green fidget spinner icon. You click that, and it will create a group, and then you can right click on the group and name it. And I will name it import or input curves or flat 4 corner curves, and create a grid on them. And then mesh from points, clean mesh, and unify normals. I group them as well and call them create mesh from grids. No, create meshes, multiple meshes from grids, join them, and clean them, right? Then the next one is show. I'll just group this and just goal show. Show the mesh after the simulation, right? That's this goal. And then I will group the edge lengths together with length factor, like this, and call it goal contract the mesh, make the mesh smaller. Then I have vertices, curve reference, in curves check, cull, and anchor. I group those and call it anchor the vertices which are inside of drawn regions. And the last one is vertex load. So it's basically apply inverse gravity. Then you have the entwine, the solver, bang, and the mesh. So honestly, I will just group the mesh node, and I'll just call it bake this. Right. If you want it to be, if you want to get it into Rhino, you bake this one. You don't bake the preview. The preview will not let you bake it. So you do that. Sorry. This Celery Automata tutorial, I'm not be giving it through this kind of webinar, but rather you'll need to look at it by yourselves. That's going to be homework. And you can find it on my YouTube channel, where it's a tutorial series that are called like 4.1, 4.2, 4.3, 4.4, 4.5, right? So these 5 tutorials, out of these 5, and they were recorded back in 2019, out of these 5, you care about, for now, you care about only the first 3. And let me just quickly guide you through what you'll see in those videos, right? So 4.1 tutorial, or 2019-1 LTH tutorials, discrete minimal surface elements. That tutorial is going to be quite familiar to what we have already done in yesterday afternoon. Here I'm just talking about how to make these kind of minimal surfaces with kangaroo relaxation, right? So this is kind of familiar. Like all of these white patches are rectangular curves, closed rectangular curves that connect, and then we just relax it, right? And here I just give a little bit more information about it, how it works, and so on. Give you a bit of a, print screen, not print screens, renders of the structures that can be done with it, and then kind of start talking about how to actually create those structures, right? So, and then you can see, the kangaroo solver, the entwine, the show, and so on. So it's kind of a repetition from what we've been doing now, only that it's a little bit more complex. So it's hour 20 minutes. You can check it out if you want to. So this one is not mandatory. The mandatory ones are, is it possible to just move this crap? Oh, it is. Okay, nice. Wait. I'm trying to figure it out. Move it here. No, that's bad. That's also bad. Yeah, fine. I'll need to have it there. Where was I? 4.2 and 4.3. These two tutorials, 2019-2D Game of Life and 2019-3 2.5D, 2.5 dimensions Game of Life. These two tutorials you should look through and you should do. First of all, because they're really cool. The structures that come out from them are really cool. Second of all, it's the part of the course. Just doesn't, we don't have enough. We're going too slow. You can guess why. I mean, it's due to the fact that I'm not in the same room as you guys. So we need to cut some corners, and you'll just check these YouTube tutorials by yourselves. So 4.2 will just teach you how to do this kind of a Conway's Game of Life setup, where it's only going to be done in two dimensions. So it's going to be a flat thing, right? A flat, I don't know, structure, not even a structure, a pattern. And here I kind of talk about the data trees and so on quite a bit. So make sure to follow through and kind of do it. And by the end of this tutorial, the 2D Game of Life tutorial, you will see something that is going to behave like this, right? First of all, it's going to be automated. Second of all, there's going to be a certain amount of behavior. And what this is called a cellular automaton, right? Where you describe how a cell, a molecule or whatever, an atom, behaves within a certain conditions, within certain conditions. And then according to those conditions, the whole thing gets animated, and the cells change their behavior. In this case, they change behavior from being alive or being dead, right? So the cells that are pink are alive, and they kind of change the behavior. I talk much more about it in the tutorial itself, so make sure to check that one out. So that's that. Let me close it. And then 2.5D game of life is a continuation of the previous one, of the 2D game of life, right? So it's a continuation. And here, all we're doing is we're basically creating a three-dimensional structure out of these shapes, right? So we're basically stacking each generation of the cells upwards, and thus we're growing. Growing these kind of towers of things, right? And by the end of that, we'll have something. You will have something like this. The beeping. I think everyone's muted, isn't it? No, it's way too far. Wait. Can it be the 3D printer? Huh. Okay. Let's see. That would be very weird. If I mute my microphone, just I will mute my microphone and let me know if the beeping stops. Uh-huh. And what about now? Is it fine now? Huh. So everyone here seems to be muted. Albert. Oh yeah, Albert's not muted. Wait. No, Albert. Oh, crap. Okay, that's my printer, guys. Wait. Wait. I will be. I'll go stop the printer, and you'll let me know if it's, if it's muted or, I mean, if it's going to make a sound or not. I assume it's not beeping anymore. Wait, let me see. Oh, crap. Okay, so wait. I can't even print now. Sucks. Do you have a headset with a mic? No, I'm using a decent microphone here. The headset with a mic kind of, usually the microphone is much worse. Well, whatever. I'll start the print later. That's fine. Minimize that, close that. Back here. So by the end of those two tutorials, the 2D game of life and 2.5D game of life, what you'll end up getting are these kind of structures, which are porous and they can be controlled to a certain extent to produce architecture later on. And I do have two examples. One of them is by me and Olga. very good architecture company.com, projects. Did this project right here, Tower of Life. We used the same approach where we kind of designed a 1 kilometer tall skyscraper by just using that cellular automata grove, right? And you can see here, like, these are all of the sections, all of the plans that we got, and this is the structure that we ended up having. What's the password? Oh man. Wait. Everyone's invited. Ah, okay. Okay. Mia is still out, but where do you find the file to what exactly? I have many Grasshopper files. You need to be more specific. In the beginning of the tutorial, Grasshopper file. Well, my Grasshopper. Oh yeah. That was a YouTube video. I was telling everyone what kind of homework you'll have, what you need to do at home. Well, you are at home, but what you'll need to do by yourselves just to save time. And it's on my YouTube channel, 2019-2. Well, actually, I can do just this. First of all, you will look at this. So this video, and then, come on, minimize. And then it's going to be this video. So these two videos and following them and being able to kind of operate with them are going to be your homework. And I'm just showing you what kind of a forms to expect from those two YouTube tutorials. And we'll make sure, of course, that you have all of the necessary plugins and that everything is running before we finish today, so that you can indeed follow through with this 2D, 2NF5, with this Game of Life tutorials. Anyway, so this was the project that me and Olga did. Just a tower, right, made out of it. We just added glazing by hand later on in Rhino. And then we have one more project. Everything is very, very convoluted. We have one more project here. Am I recording? Yes, I am. That's good. So it's in the course website. If you scroll down, then one of the examples are this project right here, which used exactly the same method and approach. Of course, in this case, it was not a tower, but rather some sort of a bony climbing structure. Right, so that's that. That's your homework. And let me, I'll just keep closing it. So now let's jump back into Grasshopper, into Rhino. And let's close, well, not close, but let's start with a fresh file, a fresh Rhino file and a fresh Grasshopper file. Right, so do that. Need to record as well. So in Grasshopper, if you want to repeat a certain, let's say, movement or any kind of method for changing geometry, or even like something as simple as addition of numbers, if you want to keep repeating it for a number of times, then you would need to either script it in C# or JavaScript or Python, or you would need to use a plugin. And the plugin that does this kind of repeating, a loop, is called Anemone. So if we, I can just show you a really quick example. For instance, let's create what do we create? Let's create a sphere. So in Grasshopper, type in sphere. Right, and let's just give the sphere a radius of 5. Right, so we have a ball. Okay, and now let's move that ball. So type in move. In X direction, for instance. So you just type in X, hit enter. So unit X, right? And then just create a slider between 0, ... and I don't know, 200, something like that. So you can move the sphere, right? Well, of course, we need to hide the original sphere and just have the preview of the moved one. And then basically, as I'm moving the slider, the sphere moves together with the slider. Very, very simple setup. I'll just give you a little bit of time to catch up. I didn't delete the original, I just disabled the preview of it. All right. So we have a sphere and we're able to move it, you know, at some sort of a number of millimeters to the side. The thing is that what if we want to, along the X axis. So the thing is, what if we want to move it in increments, right? So what if we want to move the sphere like animate the movement of the sphere? So every step of the animation, the sphere moves by 1 unit or whatever, right? Then we can't really do it because, well, we can kind of manually keep dragging the slider and it's going to be moving, but it's not really correct, is it? Right? So instead, we need to loop the information so that we take the sphere and we move it by 5 mil. We take the sphere, we move it by 5 millimeters. Then we take the moved sphere, we move it again by 5 millimeters. Then we take the moved sphere, we move it again by 5 millimeters. So we keep adding 5 millimeters of movement to our sphere. So that setup would look like this. Delete the move, delete the X, and delete the slider. Just keep the original sphere with radius of 5 in your files. Something like that. Okay. And let's use anemone. So type in loop start, and also type in loop end. Loop start and loop end. So these two nodes. Everything that happens in between these two nodes is going to be repeated, is going to be looped, right? So we need to go through the inputs and the outputs of them to see how they need to be set up, right? One by one. First input is number of repetitions. So how many times do you want to repeat something? In this case, the movement. I'll just create a slider and I'll just say, I want to repeat it 100 times. And just connect it. Right? Then we have a trigger. If you want to loop to restart, you can trigger the loop to restart. So the trigger is a button, right? Just like in Kangaroo, we have restart button. Here we also have a button to restart the loop, the simulation, right? It's like that. And D0 is what kind of data, I don't know. What kind of data do you want to use to loop, right? What is going to be changing? And in this case, what's going to be changing is the position of our sphere, right? So our sphere is going to be changing. So I'll just take the sphere and plug it into D0 input, like so. Okay. And now we have 3 outputs from loop start. First one is, it just says connect to loop end. Okay, and the loop end one says connect to loop start. So we have like two things that just want to be connected. Yeah, sure. We just connect them. That's fine. The next output of loop start is a counter. So it's basically, right now it says null because the loop is not running, so it doesn't have a number, but it's basically going to generate a number for us, right? At this stage, we don't need it, but at later stages, especially in that Game of Life tutorial that you're going to look at by yourselves, we will be using the counter. So what counter says is every time when the loop is running, the counter will count which step or which step of the animation are you currently at, right? So it's just going to go every time when the loop finishes and starts again, it's going to add +1 to the counter, right? So it's going to keep counting how many loops has it's done. For now, we don't need it. And D0 is basically stuff that comes into D0 here is going to come out from D0 here. but that is only going to happen for the first loop, right? For the first repetition. Once the first repetition is done, oh, actually, yeah, let's do it this way. Let's just create a brep component. Brep is boundary representation. So it's basically the same thing as polysurface or a surface. So empty brep component, connect D0 to it and connect it to D0 from loop end. My English is breaking. Okay. So you have a setup like this, right? And if I click the trigger, you know, the button, everything is not going to be orange anymore as long as I click the button. But nothing is really going to be, you know, changing, because the way this works right now is like that. So the way this works, this setup works, is a sphere. So this sphere is created, right? And it goes into the loop start, and it happens during the first repetition of the loop. Then what it does, it spews out the same sphere, right? So it carries over here into a brep component, which doesn't change anything about the sphere, so it just continues on. It arrives at D0 here at the loop end, and it goes back into the loop start, right? And then it spews out the same sphere at D0 again, and kind of continues on like so, right? So it keeps doing it over and over again for 100 times, right? So since we're not changing anything, yes, you can, but I connected the brep just to show you, you know, that we are operating with geometry rather than something mysterious. But yeah, you can directly like just do that without the brep whatsoever. So now it's hard to see, you know, what's going on. So I will be changing the position of the brep. Every time when the loop is running, I will move the brep in X direction by 2 millimeters. Something like that. So now what's happening is, well, let me just then run the simulation for you so that you can see. It's going. Still going, yeah. Now I reset it again, going. So now what's happening with this is we have a sphere, right here, and we have the loop start. So the sphere goes into loop start, and I'm talking about the first step of the, I'm talking about the first step of the simulation, right? Or not simulation, the first step of the loop. So it goes right through the loop start into this brep component, and it gets moved by 2 millimeters to the side, right? And then the moved version, so not the original, but rather the moved version, goes into the D0 input of the loop end, which means that for the next step of the loop, it's not going to be using the old sphere, but rather it's going to be using the moved version. And it's going to move that version by 2 millimeters again, and going to repeat it and move the moved version by 2 millimeters again and again and again, and it's going to do that 100 times, right? So every time when I hit reset, it just goes, right? So it's going. Not very exciting, but a lot of potential, right? So that's how loops work. To have a bit of a more interesting, I guess, approach, should we do it though? Wait, I'm thinking if we should do something that's uncontrollable. No, because you will come up with quite broken geometries if I show you that. And we won't be able to, like the remainder of the course is going to be us fixing the geometries. So that's not going to work. Tell you what, if we have enough time on Wednesday, I will show you one more thing, and it's going to look like swarm geometry. It's going to look like, there we go. You know, crap like this. Borderline impossible to control. Looks nice, you know, or at least kind of nice, but borderline impossible to control and to kind of work with. But I noticed that the students really like trying it out, but by the end of the course, they just pull their hair out trying to, you know, make architecture out of it. Because all that you can get from this is a bunch of curves. And even that is not that nice of a curve. I mean, even this, whatever. So if we'll have enough time, I will show it tomorrow. For now, let's keep it somewhere. Just disable preview. So just select everything here and disable preview of everything. And let me show you Cocoon instead. That is much nicer. So for Cocoon plugin, we need some sort of an input from Rhino. So I will be just creating 2 points in Rhino. These 2 points here. It doesn't matter where they are, just kind of close to each other, right? So these 2 points here. I will create a point component in Grasshopper and right-click on it, set multiple points, and select the 2 points, hit enter. So now they're referenced in Grasshopper. I guess before we begin, I should explain what Cocoon does. So Cocoon is what's called a marching cubes based mesher, meaning that it can generate clean, well, relatively clean geometry out of any forms, and it can merge any forms into one single closed geometry. So if I were to Google Cocoon mesh, Grasshopper, right? And if we were just to look into the images of it, yeah, this guy is, I guess, the easiest to understand. You know, you have a curve, and you have 1, 2, 3, 4. You have 4 points on the curve, and everything is being merged in a very clean way. a more advanced version of Cocoon, or not Cocoon, but how to use a Cocoon are these kind of things, right? This is just basically a crap ton of points, right? And then you can use that to generate these kind of cave systems and so on, or you can use curves and make some really interesting stuff with them. Yeah, so that's basically Cocoon meshing. And I'm trying to remember if we have any. Have we done anything with Cocoon? That's cool. No, we just use it to clean up stuff. But that's fine. I will show you how to work with it right now. So we have 2 points. Actually, let's just create a curve as well. Oh, that's not a curve, just a nice curve. Something like that. And just reference in the curve as well into Grasshopper. So we have a curve and 2 points. Now we want to create a single closed geometry out of these 3 things, right? Out of these 3 objects, and that's why we are using Cocoon. So in the Mesh tab, right in the top, Mesh tab, Cocoon subtab, you have, what is it, 6 different tools that you can choose from. The first 2 are basically, the tool that's called Cocoon is the brain of, like the solver of the plugin, and Refine is additional tool that helps you, refine the geometry once it has been solved, so to say. Then you have, so these 2 are something that happens by the end of our approach. And then you have BREP, boundary representation charge. You have curve charge, curve group charge, and point charge. In this case, we will be using point charge for our points, and we will be using curve charge for our curve. So just put those in. Under mesh, it's under params, math, surface, blah blah, mesh. Okay. So slowly, point charge, curve charge. The first input of the point charge is it asks you for points. Yeah, sure, we will give it points. We just connect our points to the point input. The next one is it asks you for a radius. So what kind of a area does each point influence? And it's basically going to create a sphere around each point, right? So what's the radius of the sphere, basically? We can say that the radius of the sphere is, I don't know, let's go for 20. I don't know, some number, 20 is fine. And then you have strength or point charge. Yeah, charge strength. So here I always use 1 unless I need to be able to change the radius of each point individually. But usually, like, especially for this, for you guys who are starting to use Cocoon, just use just number 1 for strength, both for point charge and for curve charge, right? So I'll just type in 1, plug that one in here. 1 for curve charge, plug that one in here. And then for the curve radius, I'll use something a little bit smaller, like 10. So we have something like this going on. Okay. So we have charges, right? So each point and the line has a certain amount of charge associated with it, and we can use those charges, which are basically it's a whole thing. I don't want to go in deep into marching cubes algorithm, but it's basically how it works, right? Or should I? Maybe I should. Screw it. Let's learn this properly. Okay. A quick break from this. Time to Google some stuff. So the way Cocoon works, it uses what's called the marching cubes algorithm, right? And the way marching cubes algorithm works is it has a library of 15 possible ways on how a polygon, a mesh, can be placed in a cube, right? That's the first important notion, right? It has 15 different cases. And if I were to break it down, how it all works, it's basically the first step is the algorithm takes the space around your geometry and it voxelizes it. What does it mean to voxelize something? Well, in 2D, it's called pixelate, right? So in 2D, you have pixels, like two-dimensional squares. In 3D, you have voxels, right? So a good example of that is Minecraft, right? Well, Minecraft. So in the video game Minecraft, the space is voxelized, meaning that everything is divided up into these three-dimensional pixels, which each of them has a certain quality attached to them. And in this case, it's mostly materiality. And so on, right? So Minecraft is voxelized. The problem with voxelized stuff is that it's all, you know, very bricky, very boxy. So to actually work within a voxelized environment and end up with a smooth surface, a marching cubes algorithm was created. And mostly it wasn't used for video games or anything like that, but it was used for forensics and for, how are those called? You know, the scans of the full body scans where they make multiple like sections of your MRI, yes, MRI scans, or CAT, yes. So these things, right? So marching cubes algorithm initially was created to rebuild information from an MRI scan, right? Because an MRI scan is basically a series of pictures, right? Which can be stacked on top of each other to recreate a three-dimensional shape. And a picture is basically, a picture is basically a grid of rectangles, which are brighter or darker, right? If you stack that grid of rectangles on top of each other, then you end up with a three-dimensional shape, which is, instead of pixels, you have voxels. And that means you can work with those voxels to extract a three-dimensional shape from series of cuts. And if I Google MRI scan, yeah, there we go, marching cubes, you can see exactly that, right? Wait, let it zoom in real fast. Oh, come on. Do we have anything? Yeah, the skull, the brain, and so on. So just trying to, yeah, there we go. That's good. So from series of sections, you can rebuild a 3D model. And that's where Marching Cubes algorithm comes in very handy, because it can interpolate those 15, where they are, those 15 variations. There we go. 15 variations of polygons and how they are assembled in a voxel grid can be used to create a very high detailed and relatively smooth mesh, which is not, you know, not this kind of, it doesn't have this kind of Minecraft aesthetic attached to it. Oh, this is actually, this actually shows you quite well how it works, right? So you have sections of the, I don't remember the English name of that bone, the pelvis bone. So you have sections of it, and those are stacked on top of each other and then meshed into a single shape, right? And we can do that in Grasshopper quite easily, but I guess it's a little bit unnecessary. What I'm getting at is marching cubes was used for medical stuff and forensics, right? So a gunshot wound to the head is much easier to kind of map out, you know, especially what's happening inside. It's much better to build a three-dimensional mesh and then use that in the court rather than pictures from opening up the corpse after he was shot. I don't remember the English name for it. Anyway, so in this case, what's going to happen under the hood in our Rhino files or Grasshopper files is that the Cocoon plugin will divide the whole space into small cubes. And it's going to decide where the mesh is going to be placed according to how strong the influence from these point charges and curve charges are. Right? We will not be able to see the resolution. We won't be able to see that kind of Minecraft, you know, those kind of Minecraft cubes will only be presented with the final result, but that's what's going to be happening under the hood. So to make this work, if you go to Cocoon and you just use the straight up the Cocoon node, like that, you have 4 inputs. The first one is charges, right? And you have 2 outputs here, the point charge and the curve charge. So if you hold down the shift key, you can connect more than one wire into an input, right? So if you hold down the shift key, you can connect both the point charge and the curve charge both into the Cocoon charges input. The second input is the target ISO value, right? So what ISO value is, come on. Okay, to be fair, this tutorial, when I'm giving it to the master students, it takes like 2 days, right? So the ISO value is basically, first of all, it's in between 0 and 1. It's always between 0 and 1. Second of all, it's interpolating how strict, yeah, maybe that's a good point of view. How strict is the Marching Cubes algorithm going to be when it's going to be dealing with point and curve charges? If a charge is something that's a very small number, will it still consider it to be a charge, or if it's a small number, will it just cut it away and ignore it? So basically, the higher the ISO value number, the closer the ISO value number is to 1, the more stuff is going to be disregarded as non-important. The closer it is to 0, the more stuff is going to be regarded as important. In turn, what you'll be observing and what you will be seeing is that the smaller the value you plug in to the ISO value, the thicker everything is going to get, and the bigger the value, the closer it is to 1, the thinner everything is going to get. So let's just do 0.500. So just a slider, 0.500. So half, right? Somewhere in between 0 and 1. It's always a good idea to start off with, these values and kind of then calibrate everything as you go. Next up is cell size. Okay, this is very easy to explain, thankfully. Cell size is the resolution of the space, right? Everything is divided up into under the hood. You won't be able to see it, but everything is divided up into, hold down the shift key. Yeah, it should work. So in here, everything is going to be divided up into cubes, into small cubes, right? Which you won't be able to see, but all of the stuff, all of the building of the mesh is going to be happening inside of those cubes. The smaller the cubes, the smaller the voxels, the higher the resolution, is going to be, but at the same time, the slower it's going to be, and so on. So you kind of need the balance. Usually, the way I work is I usually go for half of the smallest radius, right? So in this case, my radius is for the curve charge is 10. So I'll go by half. So I'll choose 5 for the cell size resolution. If I need to, I'll make it smaller later. And then the last one is execute. Would you like to execute the algorithm? So we just toggle, Boolean toggle, and plug that one in and toggle it to be true. And we end up with something like this. Not too fancy, but as I always say, you need to start off with low resolution so that you have a higher degree of control. And then once you kind of know what's going on, you can increase the resolution, right? So in this case, let me show how it behaves. Let me grab the point here and let me slowly move it closer and closer to the curve. See how as I move the point towards the curve, it's the whole thing starts stretching out. Oh, actually, I will increase the resolution by decreasing the cell size to something like 2. So you can see now it's much more polygons, but it's going to be easier to see. As I'm moving the point towards the curve is starting to bulge, and the sphere is starting to bulge. And if I move them beyond a certain threshold, they will just meet, and they will become a single mesh, right? So this is how it works. Board, chat, something in Swedish, don't care. Okay, continue. So to make something nicer, for instance, I will just delete everything. Well, not everything, everything that I have in Rhino. And let's say, let me just quickly make something a little bit nicer for you to kind of check out. So I can do something like boom, 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 something like this, and maybe it's doing that, and I can kind of use polar array polar. 5 items, whatever. So I have something like that, and I use that as curves, set multiple curves. So we end up with something like this. Let me increase the cell size a little bit. It's a little bit too wonky. And then I can keep, I can keep adding things. So I can say that, I need a few points here and there, whatever. For some reason at the base, I need like 5 points. So it becomes something like this, and then I have no idea what I'm doing. So maybe we do something like that, and then rotate this by 30 degrees. Was it 30? Yeah, good enough. Rotated by 30 degrees. More curves. And maybe increase the radius of the curves to be a little bit higher, or no, maybe not. So you can end up doing something quite fancy, I guess. Well, not necessarily fancy, but something rather complex really quickly. Wait, am I messing it up? I am. What's going on? Let me just finish up here, and I'll just then I'll just look at the chat. Just want to let me just move it. F10 control points, control points, control points, control, control. Move it up. There we go. And then maybe we have a curve going through here. Clear values, set multiple curves. So we end up with, this kind of a nonsense. Right now, I didn't think, what I was doing, so it's uncontrolled, but. Yeah. If they are fat with the same numbers, it means that they are smaller, right? So this is the radius is in millimeters. Am I recording? Yes, I am. Drawing smaller scale. And I got the curves in the circle by using array polar tool. Okay, so we end up with something nonsensical like this, and Actually, I would probably go back into here and just, I really don't want to play too much with this, but I just can't leave it, you know, so screwed up. Yeah, that's fine. Okay, so we end up with, you know, some sort of a shape like this. And there is a certain amount of cleanup that we need to do to make this nicer, because here it's a little bit, you know, broken down. Can you check if you have a smooth mesh tool? Not just smooth, but a smooth mesh. It has like a orange icon with bubbles and so on. Yes, 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 yep, 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 yes, 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 yep, yep, yep. Okay, good. So let's use smooth mesh. Let's use that one. And it works exactly like it does in Rhino, right? So it takes the points of the mesh and it kind of moves them so that it moves them according to the neighbors that the points have, right? So for mesh smooth, I will just connect my sorry, my cocoon mesh output to my mesh smooth input, like so. I will make sure that I hide everything except my mesh smooth. And here I have more options. What the, oh yeah, that's good, that's good. I have more options. I have the strength for smoothing, and I would suggest not messing with the strength. 0.5 is fine. It works most of the time quite well, so don't mess with it. Then you have with skipping naked edges. In this case, we don't have any naked edges and we will not have any naked edges, so we don't care. And we have iterations. So this is basically how many steps will it do for smoothing. Rule of thumb is somewhere between 1 and uh, 1 and 15 steps. You don't want to go further than that. The higher the step count, the slower it's going to be. So I'll just do like 5 steps of smoothing. Oh yeah, and also with every smoothing step, it's going to become thinner and thinner. That's also a thing that happens. Right? So 5 steps. And there is a limit for maximum change in the structure, but we don't care about that limit. So we can see here that even though we are using smooth, it's not smoothing it out that well. And that is because this geometry that we have here is the polygons are arranged in a very funky way. And it cannot smooth it properly because the topology of the geometry is not great. You know, it's not, while it is a perfectly 3D printable geometry and it's clean in that regard, the topology of it is not clean. So the arrangement of how the faces are arranged are not clean. To fix it just a little bit, in between the cocoon mesh and the mesh smooth, we can use Weaverbird's Catmull-Clark subdivision. So if you go to Weaverbird tab, WB, if you go to that tab, and you go to sub-D sub-tab, there you will find Weaverbird's Catmull-Clark subdivision. And in between the mesh smooth and cocoon, we can use this Catmull-Clark to kind of mitigate a little bit of that, you know, bumpiness in the structure. So I will just connect my cocoon M output to my Catmull-Clark M input and connect my Catmull-Clark O output to my mesh smooth M input. And now it's a little bit better. It's always going to have that kind of a little bit of Ripley effect. It's just something that we can't get rid of easily. But at least now it's a tiny bit better. I wonder how refine would work. While you're doing it, let me just check this refine. Mm-hmm. Mm-hmm. Yes, but at the same time it gets heavier. So at a certain point, if you if you decrease the cell size, you end up getting more and more polygons. But at a certain point, your computer is just going to say no, right? So there is a trade-off. It becomes much slower. I'm just trying out the refinement. Just a second. Hmm. Maybe I should. Okay. Ah, man, that's a lot of stuff to give you in a okay. Let me show you an alternative way, which apparently is a little bit better. And it is incorporated in Cocoon. So Cocoon refine the output from Cocoon, right? This guy right here. It has a lot of inputs, and we will be going through them. I will be explaining what they do. So let's start from the start. Refinement data. Explanation of it, refinement data from Cocoon. Okay, we have no idea what it's doing, what it's asking us of, but Cocoon node indeed has refinement data output. So I will not be asking any questions anymore. I will just be connecting Cocoon refinement data into refinement data input. You know, samples. Maximum iterations to sample vertex against ISO. Okay, so the way ISO values work is that they are relatively infinite, I guess, in resolution, and vertices are not, right? So as vertices are being created, they're kind of, they have this kind of step size at which they need to be placed. So maximum iterations to sample a vertex against ISO is basically when refinement is going to kick in, when this node is going to kick in, it's going to start slightly moving the points of the mesh around so that they resemble the ideal version of that mesh much better. So this is how many times does it try, right? And let's just say 10, right? So just slider 10. So it will go 10 times over it, and we'll try to kind of polish out the geometry as well as it can. Next one is sample size. So sample size is basically, How big of an influence radius does each point have around it? Each point of the mesh. So each point right here, where the edges meet, you have a point of the mesh or a vertex of a mesh. How big of an influence does it have? Right, so here I will just say like 1 millimeter, right? So it doesn't have a lot of influence. So it's basically, it cannot be moved really far, but far enough for all of this to become a little bit smoother. So 1 millimeter should be fine. Then you have sample tolerance. Man, this is at what distance does the refinement node say that, yeah, this is good enough, right? Sample tolerance. I will say that sample tolerance should be 0.1 millimeters. So if each point of it is closer than 0.1 millimeters to the ideal mesh, to the perfect, form, then it's going to say, yeah, this is good enough, 0.1 millimeters. Then we have Laplacian smoothing. I can show you what it does through an image. Laplacian smoothing. So you have a mesh, right? In this case, it's a mesh with with 5 polygons, which are triangular, right? And right in the middle, you have a point, a vertex, which is off center. What Laplacian smoothing will do is it will just scooch it so that all polygons are kind of the same size and the vertex is in the center. Very simple diagram with 5 polygons, but in reality, it kind of usually looks like that. It just smooths everything out, and you even get dimples from time to time. But it is smoothing, and here it's asking for number of Laplacian smoothing passes. So how many times will it go through the geometry and try to smooth it out? And I will just say, yeah, just go through it like 5 times. I don't know. If I need it to be smoother, I will increase it. Keep in mind that Laplacian smoothing will shrink the geometry a little bit. So the more you increase this number, the thinner everything is gonna get. Then we have valence passes. Oh God. So valence is mesh valence. That's not how you write valence, but that's good enough. This is a good table. I can use it. Iterations will stop helping with smoothness if you have the tolerance, like tolerance and the sample size. These two guys are stopping the smoothness of over smoothing, right? The sample size and sample tolerance are basically breaks which don't let the shape to change too much, and it's important to have those breaks, or else it is going to, the mesh itself is going to start messing up if it gets too thin and if it gets smoothed too much. So back to valences. You can see valence 3, valence 4, valence 5, valence 6, right? So valence 3 is when you have a single point, a vertex, that is shared between 3 polygons. Valence 4 is a vertex that is shared between 4 polygons. Valence 5, vertex shared between 5 polygons, valence 6, vertex shared between 6 polygons. Kind of easy. The thing is that we really like when there is valence 3 and valence 4, right? That's really easy to later on. Those kind of meshes are later on really easy to divide into, for instance, stripes, into strips, and laser cut them out and so on. When you have valence 5, these kind of arrangements of mesh faces, it becomes kind of problematic, because then you kind of need to start. Well, you can see here even the direction of the mesh, which is shown with an arrow in the bottom. So here it's just it just goes right. It's just a triangle, so it can just go through. If you have valence 4, it needs to make a bend, right? If you have valence 5, it starts doing this zigzag, or it can do it can make a branch, or it can do a zigzag in the opposite direction. With valence 6, you don't have you always get branching of the directions of the stripe. So if, for instance, if you're doing a mesh, if you're preparing a mesh for production, just like Mark Fornes, where is that? Google again, Mark Fornes. Oh, hey, Mark. Yeah, whatever. This kind of, yeah, this is even better. Let me, come on, minimize. There we go. So these kind of structural stripes, right, which are flowing along the mesh, if you have valence 6 somewhere here, those stripes would need to, they would become really weird. They would need to branch out, and there would be a lot of problems involved with it. So usually different programs use these kind of algorithms which take care of valences, and they try to do to remake a mesh with valence 3 and valence 4 vertices. In this case, it's here, valence passes. Number of iterations to fix valences. It doesn't even say, that those are okay variations. Those are just something that needs fixing. And for that, I will just say, yeah, just try once, right? Try one time to fix it. If you can't, then screw it. Alternatively, you can use something like 10 for it as well, if one doesn't work. But in this case, we are not going to be making any structural stripes out of this, so we don't care. 1 is fine. And then we have subdivide, number of times to subdivide. This is the same thing as Catmull-Clark subdivision, right? So I will just say, yeah, subdivide it once. One time. Last one is execute. I will just toggle, Boolean toggle, turn it on. And you can see how much smoother this thing became. I can bake out this mesh from refinement, place it here. And just looking at it. Oh, I know what I can do. I can bake out before the refinement and after the refinement, just to show you the differences between them. So on the left-hand side, the mesh is before refinement. On the right-hand side, it's after the refinement, right? So you, at least from how the polygons are arranged, you can see the difference, right? You don't end up having these, shit parts here. But at the same time, since we're still using only one pass for fixing valences, in some cases, I end up with, let me just quickly mark it out for you so that you can see what I'm talking about. Come on, Jesus Christ. How do I show it? Extract mesh faces. There we go. So in some cases, you still get these kind of awkward single point, valences that are not that great. But that's okay. Again, we are looking into 3D printing, not structural loop creation. So, as you can see, this is a pretty powerful tool that can be used to create a lot of organic shapes. And all that matters is what kind of geometries you plug in there, right? Questions? No questions, huh? Strange. Oh, there we go. Oh yeah. Can you send me Philip's project? What can we do to make the volumes into more detailed objects? Make it more human scale. Later. Does she though? That's something that the teachers in the academia tend to say, especially the older ones. I mean, all of the buildings that I've seen, maybe. They are big. Calatrava is great at that. Wait. We will come back to that question in a bit. I just want to show this project real fast, and then we'll talk about the what can we do to make the volumes into more detailed objects. Yeah, I will come back to that. That's actually a very important question. But now Olga has sent all of you a link to see her classmates. Yeah, her classmates back when she was studying her master's work with exactly the same approach as I was showing you now, right? So actually, yeah, to answer the question of what can you do to detail it out more, to introduce detail at a more human level, yeah, just add more curves, right? And it's just going to be detailed. So this was an exploration over capturing the Gothic line. That's very poetic. But it was an exploration over the ornament and architecture and how you can use ornament as something that's structural. And you can read through this. This is actually a pretty damn good project. and all of the possible ways of how you can connect things. And the beauty of it is that it's achieved through something that is so simple, right? It's just curves and cocoon mesh, right, that connects the curves. So all that matters is how you, what kind of curves do you draw, right? And these are drawn by hand. Well, in Rhino, but these are drawn in Rhino rather than simulated in some way, right? So it's all, just messing around with the form. Oh, and then there's more stuff here, which is not, yeah, that other stuff is not important. Don't look at the other stuff. Look at the curves. That's very nice. I think I saw some questions here. Oh, yeah. No. Yes, kinda. If you try to make this mesh into a closed solid polysurface, it will not work. It will work, but your computer will not handle it. It will crash your computer, unless you have a really strong computer. Because it's what it's going to do, it's going to take every polygon and it's going to make a surface out of every polygon. So imagine, how heavy it's going to be, that polysurface that you get. There is the whole commercial industry that is aimed towards bringing mesh geometry into, or translating mesh geometry into NURBS geometry. And those kind of software packages cost a lot of money. So there are ways on how to do it, but they are hard to do, and they are quite tedious. It is, though, quite easy to make a mesh out of a NURBS polysurface. You just type in mesh in Rhino, and it just makes it into a mesh. But usually when working with these two geometries, these two types of geometries, you want to work with them kind of separately and understand the limitations of one and the other. Meshes are much faster, so you can achieve much more complex results with meshes. With NURBS polysurfaces, you can be much more accurate. It is not to say that with meshes you cannot be accurate. You can go, like 0.01 millimeter tolerance, and then it doesn't matter anymore if you're, 0.01 millimeter off in your architectural model. So that's one thing. The reason why it's very hard to get a NURBS polysurface from a mesh is because meshes contain much less information. So it's hard to create information from nothing, right? While it is very easy to make a mesh from a NURBS polysurface, because all you need to do is you just need to remove a lot of information, right? So that part is easy. When working with architecture, and I have it here, where do I have it? Right now with my master students, I'm just trying to, let's see here. Just try it. Do we have it here? Maybe no, that's just that. Oh, yay. The webinar has been uploaded, by the way, from yesterday. Anyway, there we go, this guy right here. So for my master students, I've been sharing this tutorial where we were indeed using meshes and generating these kind of forms with meshes, right? And then I told them to actually use a command that's called mesh to NURB to create a NURBS polysurface from these meshes to be able to use Booleans and so on. To be able to do that, you need to have very, not very, but quite low resolution mesh, right? And then you will be able to do that. So what I'm getting at is, if you have 1 million polygons, right, it means it's going to make 1 million surfaces. But in reality, in architecture, in a building, you will never have 1 million surfaces. It's always going to be some sort of a paneling system, and it is going to be architecture in itself is somewhat low resolution. So if you're planning on changing the mesh into a polysurface later on, you need to be very mindful of it at early stages and use lower resolution approach. So in this case, I would say subdivide is turned off first of all, and cell size is turned to, well, 3 is actually kind of okay, I think. Yeah, let's try. So I'll big this guy out, and I'll come back to introducing more resolution to the buildings in a bit, but more human scale to the buildings in a bit. But so you can see the difference between these two, right? So this is the ideal mesh that I would be using for rendering and so on. And this is a mesh that I would be using to change it to a NURBS polysurface. And if I just select it and type in mesh to NURB, and that I'm doing that in Rhino, and I hit enter, and I wait, and I wait, and I wait a little bit more. Yep, there we go. And then I just delete the mesh. So now this guy right here is a NURBS polysurface, which means I can use all of the, oh, that's not, it's completely missed it with the box, but I can, for instance, do some sort of a Boolean difference operation with a box on it. And it's still, notice how slow it, okay, I am recording a video and I am, streaming this, but still it's pretty slow. Oh, let me call you in a bit and then we'll continue.